Welcome to Understand the Math. In this Calculus 1 video, we're learning how to model real-world situations using exponential growth and decay. We'll start with the general exponential growth and decay model and see how it's derived from a differential equation. We'll then walk through examples including population growth, radioactive decay, and Newton's law of cooling. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by looking at the exponential growth and decay model. We're going to let y be a quantity that grows or decays over time. In nature, it's common for this quantity y to grow or decay at a rate proportional to its current size. This just means that the rate of change of y is equal to k times y. That's just a way of saying that it's proportional to y. The quantity y grows exponentially if k is greater than 0, and it decays exponentially if k is less than 0. K is just called the growth or decay constant. dy dt is equal to k times y is called a differential equation, and its solution is y is equal to y at 0, that is the initial amount of the quantity, times e to the kt. Let's now walk through 3 examples that have an exponential solution just like this model. We're going to look at an example involving the growth of a population of bacteria. With population growth examples, the rate of change of the population is proportional to the current population. The population is then equal to p at 0, which is the initial population, times e to the kt, where k is called a relative growth constant. Let's now look at the growth of a population of bacteria. We're told that a bacteria culture initially contains 150 cells and then grows at a rate proportional to its size. After 2 hours, the population has increased to 600 cells. We want to first find an expression for the number of bacteria after t hours. Let's start by letting p equal the number of bacteria at time t. In our problem, we are told that the bacteria culture initially contains 150 cells. So that means that p of 0 is going to be 150 cells. It's always good to put units with it. And then we're told after 2 hours, the population has increased to 600 cells. So that tells us that p at 2 is 600 cells. We are told that the population grows at a rate proportional to its size. That means that the rate of change of the population, dp dt, is equal to some constant k times p. This is a differential equation, and the solution to this equation is p of t is equal to p at 0 times e to the kt. Here's our p that we want to find. P of t contains p at 0 and k. We were already told that p of 0 is 150 cells, and then we can use the fact that p of 2 is equal to 600 to find k. Let's start by just plugging in what p of 0 is. So we have p of t is p of 0, which is 150, times e to the kt. Now we're going to solve for k. Let's plug in that p of 2 is equal to 600. So we have p of 2 is 150, e to the k, and then t now is 2. And this is equal to 600. Let's go ahead and divide both sides of the equation by 150. So we have e to the 2k, is equal to 600 divided by 150, which is equal to 4. Now we need to solve for k. We're going to do that by taking the natural log of both sides of the equation. So we have natural log e to the 2k is equal to natural log of 4. We can pull the 2k out in front. That's just a property of logarithms. And then on the right, we still have natural log of 4. Natural log of e is 1. So we have 2k is natural log of 4. And then we can solve for k. And we have that k is 1/2 natural log 4. Now what we're going to do is plug this expression back in for k. And we get p of t is 150 e to the 1/2 ln 4 times t. Now we're just going to change around the variables in the exponent. So we have 150 e to the natural log 4 times t over 2. And we're going to group this part together because that is actually equal to 4. So we have 150 times 4 to the t over 2. Now we're going to go ahead and simplify this, and we'll just flip the 1/2 and the t. So I'm going to write this as 150 times 4 to the 1/2 times t. And then 4 to the 1/2 is just the square root of 4, which is 2. So we get 150 times 2 raised to the t power. And that's our expression for the number of bacteria after t hours. Let's now find the number of bacteria after 4 hours. This is a lot easier. All we have to do is take our expression that we found for p and substitute in that t is equal to 4. So let's write down our expression for p. P of t is 150 times 2 to the t. Now we're going to plug in that t is 4. So this gives us 150 times 2 to the 4th. This is 150 times 16. And when we multiply that out, we get 2,400. And we need to put units with this, and it is in terms of cells. This tells us that after 4 hours, there are 2,400 cells. Let's now look at part C. We are going to find the rate of growth after 4 hours. Whenever you see the word rate, that means that we are going to be taking a derivative. Let's start by writing down what our population is. Our population of our bacteria is P is equal to 150 times 2 to the T. The rate of growth then is dp dt. And that's the derivative with respect to time of our right-hand side, 150 times 2 to the t. Over here on the right, I'm going to write down a formula. The derivative with respect to t of a raised to the t is just a to the t times the natural log of a. Let's now use that formula. So we have dp dt is equal to 150 times 2 to the t times natural log 2. Now we want to find dp dt when t is 4 hours. So dp dt when t is 4 hours is going to be 150 times natural log 2 times 2 raised to the 4th power. When you put this in your calculator, we get an answer of approximately 1,664 cells per hour. This tells us that after 4 hours, our bacteria are increasing at a rate of 1,664 cells per hour. Now let's look at the last part. For this part, we want to find when will the population reach 12,000 cells. Whenever you see the word when, that means we are going to be solving for time t. Our population of bacteria is 150 times 2 to the t, and we want to see when this is going to equal 12,000 cells. So we are going to be solving for t. Let's first go ahead and divide by 150. So we have 2 to the t is 12,000 divided by 150, and that is actually 80. Now to find t, we need to get t out of the exponent, so we're going to take the natural log of both sides. So we have natural log of 2 to the t is natural log of 80. We can pull the t out in front, so we have natural log of 2, and on the right-hand side, we have natural log of 80. Now we're just going to solve for t, and we get that t is natural log of 80, all divided by natural log 2. When you put that in your calculator, you get an answer of approximately 6.32 hours. In 6.32 hours, the population of bacteria will be equal to 12,000 cells. We started with 150 cells, and now after 6 hours, we have 12,000 cells. And that's because the population is growing exponentially. We are going to look at an example involving the radioactive decay of iodine-131. With radioactive decay examples, the rate of change of a substance Q is proportional to its size. And Q is equal to Q at 0, that is just the initial amount of the radioactive substance, times E to the KT, and K is the decay constant. With radioactive decay examples, the rate of decay is expressed in terms of half-life. Half-life is just the time required for half of any given quantity to decay. Let's now look at the radioactive decay of iodine-131. We're told that the half-life of iodine-131 is 8 days, and we are to suppose that we start with a 200 milligram sample. We want to first find an expression for the mass that remains after T days. We'll start by letting Q be the amount of iodine 131 at time T. We're told that we start with a 200 milligram sample, so we can say that Q at 0 is equal to 200 milligrams. And then we're also told that the half-life is 8 days. That just means that the amount of iodine at 8 days is going to be 1/2 of the amount that we started with, which was 200. So this tells us that Q at 8 days is going to be 100 milligrams. I'm going to go ahead and highlight both of these because we are going to need these when we find what Q is equal to. The rate of change of any radioactive quantity is proportional to its size, so we can say that dQ dt is equal to K times Q, and that just means that Q is equal to Q at 0 times E to the KT. We know what Q of 0 is, so we can plug that in, and we can say that Q is 200, that's just Q of 0, times E to the KT. Now all we have to do is find K, and we can use that Q of 8 is equal to 100 to get that. Q of 8 is then 200 e to the k times 8, and that is equal to 100. Let's divide both equations by 200. So we get e to the k times 8 is equal to 100 over 200. So that's just 1/2. We are solving for k. And to do that, we are going to have to take the natural log of both sides. That'll just get k out of the exponent. So we have ln e to the k times 8 is natural log of 1/2. We can pull the 8k out in front. So we have 8k ln of e is ln 1/2. Natural log of e is just 1. So this gives us that k is equal to natural log of 1/2, all divided by 8. Now we're going to go back up to this expression right here, and we're going to substitute in that k is natural log 1/2 over 8. So we have q of t is 200 times e to the 1 over 8 times natural log 1/2 times t. Now let's regroup what is in our exponent. I'm going to write this as e to the natural log 1/2 times t over 8. And then we know that e to the natural log of 1/2 is just 1/2. So this is 200 times 1/2 to the t over 8. And that is our expression for the mass that remains after t days. We now want to find out how much of a sample remains after 24 days. Let's write down the expression for Q that we just found. We found that Q was equal to 200, 1/2 to the t over 8. Now we're going to substitute in that t is 24. So our amount of iodine at 24 days is equal to 200 times 1/2 to the 24 over 8. So this is 200 times 1/2 cubed. So this is just 200 over 8. And that is equal to 25 milligrams because our iodine had a unit of milligrams. So we now know that after 24 days, we have 25 milligrams of iodine 131. Let's look at the last part. We want to know how long will only 5 milligrams remain. Whenever you're asked for how long, that means you're going to be solving for time t. Let's again start with our expression for Q. That's our iodine. So this is 200 times 1/2 to the t over 8, and we want to know when is this going to equal 5 milligrams. Let's go ahead and let's divide both sides of our equation by 200. So we have 1/2 to the t over 8 is 5 over 200, which is just 1 over 40. Now to solve for t, we need to get t out of the exponent, so we're going to take the natural log of both sides. So we have natural log 1/2 to the t over 8 is natural log of 1 over 40. We can now pull the t over 8 out in front. So we have t over 8, natural log 1/2 is equal to natural log of 1 over 40. Now to find t, we're going to multiply both sides of the equation by 8 and divide by natural log 1/2. So we get t is equal to 8 natural log 1 over 40, all divided by natural log 1/2. When I put this into the calculator, I get that this is approximately 42.6 days. So in 42.6 days, there will be 5 milligrams of iodine 131. We're going to look at an example that involves the cooling of a cup of coffee. Newton's law of cooling is used to model the temperature of any object that changes over time. It tells us that the rate of change of the temperature is equal to K, which is just called the cooling or heating constant, times our temperature T, that's just the temperature of the object at time T, minus T sub S, and T sub S is the temperature of the surroundings. The temperature of the object is then equal to the temperature of the surroundings plus the difference between the initial temperature of the object and the surroundings times E to the KT. Let's now look at the cooling of a cup of coffee. We are told that a freshly brewed cup of coffee has a temperature of 200 degrees Fahrenheit in a room that is kept at 70 degrees Fahrenheit. After 15 minutes, the temperature of the coffee has cooled to 160 degrees. We want to use all this information to find an expression for the temperature of the coffee after T minutes. Let's start by assigning T to be the temperature of the coffee at time T. Let's now write down what we are given. We are told that the temperature initially is 200 degrees Fahrenheit. So we have T sub 0 is capital T of 0, and that is 200 degrees Fahrenheit. We are told that the room that the coffee is in is 70 degrees Fahrenheit. So we say that T sub S, that just means the temperature of the surroundings, is equal to 70 degrees Fahrenheit. And then lastly, we're told that after 15 minutes, so that is T at 15, our temperature is 160 degrees Fahrenheit. The temperature of any object that cools obeys Newton's law of cooling, and that tells us that the rate of change of the temperature, that's d of capital T dt, is equal to K times T minus T sub S. The solution then to this differential equation is T minus T sub S is equal to T0 minus T sub S times E to the KT. So that tells us that T is equal to T sub S plus T sub 0 minus T sub S times E to the KT. Now we can go ahead and plug in for T sub S. That is 70 degrees. And for T0, that is 200 degrees. So our temperature T of T is equal to TS, which is 70, plus T0, which is 200, minus TS, which is 70, times E to the KT. So we have T of T is 70 plus 130 E to the KT. Now what we have to do is find K, and we are going to use this last piece of information to find that. Now we're going to let T be equal to 15, so we have T at 15 is 70 plus 130 E to the K times 15, and this is all equal to 160. Since we are solving for K, let's go ahead and let's subtract 70 from both sides. So we have 130 E to the K times 15 is equal to 160 minus 70, which is 90. Now let's divide both sides by 130. So we have E to the K times 15 is 90 over 130, and we can just write that as 9 over 13. To find K, we are going to have to get K out of the exponent, so we're going to have to take the natural log of both sides. So we have natural log E to the K times 15 is equal to natural log of 9 over 13. We can pull the k times the 15 out in front. So we have k times 15. Natural log of e is natural log of 9 over 13. Natural log of e is just 1. So let's find k by dividing both sides of the equation by 15. And we get that k is equal to 1 over 15 times natural log 9 over 13. Let's now go back up to our equation for t, and we can plug in what k is. So we have t of t is 70 plus 130 e to the 1 over 15 natural log 9 over 13 times t. Now we're going to regroup some terms in our exponent. So this is 70 plus 130. We're going to write this as e to the natural log 9 over 13 times t over 15. And we end up with 70 plus 130. E to the natural log 9 over 13 is just 9 over 13 raised to the t over 15. And that is complicated, but that is our final answer, and that is our expression for t. We are now going to find out what the temperature of the coffee is going to be after 30 minutes. Let's write down our equation for our temperature. T of t is equal to 70 plus 130 times 9 over 13 raised to the t over 15. To find the temperature after 30 minutes, we're going to let our time t be equal to 30. So this is t at 30 is equal to 70 plus 130 times 9 over 13 to the 30 over 15. So this is just 70 plus 130, 9 over 13 squared. When you put that in your calculator, you end up with an answer of approximately 132.3 degrees Fahrenheit. So after 30 minutes, the coffee has cooled to a temperature of approximately 132.3 degrees Fahrenheit. The last question that we're going to look at is when will the temperature be 100 degrees Fahrenheit? Whenever you're asked to find when, that means you are going to solve for time t. So let's go ahead and let's start by again putting down our equation for our temperature. We have t at t is 70 plus 130, 9 over 13 raised to the t over 15. And we want to know when this is going to be equal to 100 degrees. We want to solve for t, so let's start by subtracting 70 from both sides of the equation. So we get 130 times 9 over 13 to the t over 15 is 100 minus 70, which is 30. Let's now go ahead and divide by 130. So we have 9 over 13 to the t over 15 is 30 divided by 130. So that's just 3 over 13. Now, to solve for t, we have to get t out of the exponent. So we're going to take the natural log of both sides. We have natural log 9 over 13 to the t over 15 is equal to natural log of 3 over 13. We can then pull the t over 15 out in front. So we have t over 15 times natural log 9 over 13 is equal to natural log 3 over 13. And we want to find t, so we are going to multiply by 15 and divide by the natural log of 9 over 13. So we get that t is equal to 15 times natural log 3 over 13, all divided by natural log of 9 over 13. And if you put that in your calculator, you get an answer of approximately 59.8 minutes. This tells us that the temperature of the coffee is going to be 100 degrees in 59.8 minutes. And that's it. You've learned how to apply the exponential growth and decay model to problems involving populations, radioactive substances, and cooling processes. To really master these applications, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.